Hello, welcome to ISAT 11, Issues in Modern Production Systems. This is lecture 8, Quality Management. First, let's look at what the definition of quality. And so for American Society for Quality defines quality as the totality of features and characteristics of a product or service that vary in its ability to satisfy given needs. So in this definition, as you can tell, that a quality does not refer to a product, but also it's also about a service. So in different operations, production or service, it all can mean a little bit differently. For example, when we are making manufacturing products, then we can look at a typical quality as either any defects, the design is good, or some other issues, or it is functioning well. All right, so that's the quality. And also we are looking at some service operations, for example, the healthcare or maybe entertainment services, or if we go to the airports, we also can look at its quality as is your need be satisfied, or is your need that is satisfied in a good way or in a bad way, right? Or in a very slow process. So they all can refer to to quality itself. And now let's first look at what's the difference between good and service. So I suggest please watch this video so you can have a better idea. And when we're talking about the service quality, typically there are several aspects of the service quality. Tangibility, which is to look at this aesthetics of a company or aesthetics of the product, how visually appealing of the company appears to the customer, or the service to a customer. Another aspect is the reliability, right? The ability to complete the service. Is the service can be on time, consistent, or error-free and every time, right? And another aspect is the responsiveness, to make sure that if the customer has a request or need or questions, it can always be satisfied, and also given enough attention or promptness to deal with their needs. And also assurance is to inspire trust and confidence. So if you have a good service, can always build the trust with customers. And another one is the empathy, so which means provide caring and individualized attention to show to the customer that a company does best to satisfy their needs. Right? So there's 5 aspects of the service quality. If you look at a product quality, so which is also the focus of this course, it also includes 2 aspects in this definition. Well, and one is the product features. So product feature means are there any design defect, right? Design defect. So everything in the production wise, in the manufacturing shop floor is all good, but there are some design defects. For example, look at this fan here. There are some design defects that it actually has such a big gap, between those. They can tell it kind of poses some kind of risks, right, for kids or for whoever operating this, that might hurt the finger or hurt the hand, right? So this is a defined defect. Well, another type of defect is a freedom from deficiencies, which means there's no manufacturing defect, which means that the design has done the job, it's good design, but the manufacturing is not making it according to the design, right? Or there's some defects in the manufacturing. So that is freedom from deficiencies. And who is responsible for it? Is the manufacturing department will be responsible for this kind of defects, right? So it's a quality issue. Well, for the product features, the design department will be taking responsibility. Another concept is the cost of quality, so which means that there will be significant cost if there are some quality issues, right? And for example, if you a car, right, you produce a wrong a bad car, either from design or from or from the manufacturer itself. If it is from design, then you may think about there will be a recall of cars, all the parts. Then there's significant cost of replacing all of those, and also it hurts the reputation of the company, right? Well, if you have the quality issues with their think about a rocket, then there will be significant cost issue with in launching the rocket. It's not just about money; it's also a cost of lives, right? So, cost, so quality is closely related to a lot of other things, including the economic part. And the reason we need to analyze the quality is because there will always be variations in processes. So most times those variations cannot be avoided. While some of the variations can be dealt with, but some variations cannot be avoided. Now let's look at what are these variations. First of all, process variations, and say we have operator 1, operator 2, and operator 3, and say, okay, operator 2 and operator 3 may have a little bit different operator step 2 in a different way. So which means that for operator 2 and operator 1, they will make the product differently, right? The final product they made will be a little bit different. Same thing if operator 3 is doing step 3 a little bit different way, then the final product will also be different in the quality, right? So only when everyone is doing the same as operator 1, in this way we can reduce all these variations. So all these variations can be varied in the process itself. And what causes those variations in the process? There are multiple ways we can cause variations. The one is technology we are using. For example, if you are using very precise machine versus less precise machine, then the quality will be different in the old machine versus new machine, because of calibration or tool wear. It can also have quality issues or variations. So technology definitely can be one, and also different people providing the same service. People might do it a different way. Even in a similar operation, it still can be a little bit different. So that can be another cause of variation. That's why if you are using robotics, it will actually reduce this part of this aspect of variation if you use robotics, right? Because we can make robots in a very close or similar way. Also, the way the method we are making things different, in the methods can also cause quality variations. And lastly, the environment the same, right? The environment can be for example, different humidity, different temperature, or different other environment factors can also cause the variation in quality. And there are two types of variations. One is random, the other one is special cause. So the random means that those are built into the process itself, and they cannot be changed. It kind of reflects a stable process, and those kind of variations is pretty predictable. So, and these variations are pretty random. You cannot find some other reasons to that cause those, right? And if you want to get rid of those variations, you either have to change a new process or figure out what are ways to reduce those randomness, right? But in general, if a process that randomness is only variation, cause, that means that process is in statistical control, as long as it is within a certain accepted tolerance or range. So that's the random variation. That is something we want, okay? Because random typically cannot be avoided. And there also another type of the variation is a special cause, which means that it's not part of the regular process, either because we change the way of doing it, or new technology, or something happened, and those kind of things that we can actually solve to reduce those variations. And so typically those causes is not part of the regular process. They can be observed in different ways. They can be improved to avoid addressing a cause alone, and also it can cause the output deviate from the normal distribution. So the process, in that case, we call it the process is no longer in statistical control, right? Statistical control. Statistical control means that we set up a range, right? A certain tolerance or range of acceptable values, and then all these variations are within those the limits, right? Well, the special cause means yes, we can set up the certain limits, but we either see a lot of the values actually are out of those limits, or we see a very weird behavior. For example, it's always increasing the value, and then it might reach or or get out of the limit pretty soon, right? So that's in that way we call it not in statistical control. And when we're talking about that, we have to, when we're talking about statistical control, we have to look at this normal distribution, because typically process variation will follow this normal distribution. So in the middle, that is the mean, right? So means the mean is something you design, right? This is a design, right? For example, dimension of the part is supposed to be this long, right? This dimension. Well, we can also set up certain tolerances, say, okay, the lower limit of a certain dimension should be here, right? And the upper limit of the dimension should be here. Now let's measure 1,000 or 10,000 parts on all these dimensions. We put all these values here. You will see it will follow normal distribution, because most of the values will be around 1.25, right? Will be around 1.25, and maybe there are very, very few the values are actually outside the limit. And when you get into each end, you'll see all these values actually decreasing, because most of the values should be around the mean that is designed, right? So this is a normal distribution for statistical control. And if we draw a control chart, you will see there's an upper control limit and also a lower control limit. There's a lower control limit, upper control limit, and also there's a center line, right? Center line, and you'll see all these values are actually, if say you measure 14 or 15 parts, you will see most of the values are actually around this center line, right? So this is the control chart. And how do we use control charts to how do we draw control charts? Typically, a control chart will include the upper control limit, lower control limit, the center line, and also those points, right, those points for each one, and data points, and also you have this sample numbers as well as attributes, right? And for calculating for drawing the control charts, we need to understand some terms here. One is population, sample, and sample size. The population means the total number of the parts you are going to observe, right? For example, we have a whole class, this is 211 class, right? We have 16 students, and my goal is to what? My goal is to say measure the height, right? Measure the height of each student, right? So 16 for this 211 class means that is the population. That is the population, because I'm not missing anyone. I'm not taking any sample. I include everyone in this study. So that is the population. Well, the sample means that, you know, instead of measuring each one of your heights, actually I'm only taking maybe 4 or 5, right? Let's say I'm taking 4, right? 4 of the 16 students, right? It's a random sample. I randomly pick 4, and that is a sample. And so then I measure these 4s, each of their height, and then use this to give an estimation of this whole class, the height, right? Well, what is the sample size? All right, we just mentioned that. Okay, I'm taking a sample of 4. How many samples I can take? Actually, I can take as many samples as I want, right? For example, okay, I can take 2 samples, right? 2 samples. First time I randomly pick 4, right? I randomly pick 4, and then after measure all those, I put those 4 back, right? I put them 4 back, and then I randomly pick another 4. Well, the second 4 samples, as you can tell that these 4, there may be overlap from the first sample. There may be no overlap from the first sample, right? So that is sample size. But for each sample, I'm picking 4. So that is a sample. 4 is the sample size, right? And you know, average, mean, standard deviation, and z-value. You should have learned that in you know, in 251 statistics. I should understand that, you know, this is the mean, and what is z? Z means how many standard deviations they actually move out from the mean, right? It's apart from the mean. Here, for example, if we have 3 sigma, means that it's three sigmas. If z equals to 3, means that's 3 sigmas away from the mean. Right, same here. If z equals to -3, means that it's this direction of 3 sigmas away from the mean. Okay. All right. So we should be you should understand how do we use normal distribution to convert it to the probability, right? For example, if I want a certain probability of good parts, then you should know what is the z-value. So z from the probability, and how do we use those, you know, tables to do that. Now let's look at, say I want a probability of 0.97 of good parts, right? And then how do I find that z-value? So now the probability I'm looking for is 0.9744. Now first I need to find out, okay, where is 0.9744? Well, this 0.9744 is actually here. And then we can find this column, I got 1.9, and this column at 0.05. So which means that what? Which means the z-value should be at 1.95, right? 1.95. Well, this is how you can find, you know, from the probability to find the z-value. We can also to use z-value to find a probability. Now, can we find a probability when z is 2.13? Well, let's look at where is 2.13, right? This is 2.1, right? 2.1. Now let's look at another digit, 0.03, which is here. Then we get 0.9834. So which means that the new probability will be 0.9834 for this z when z equals to 2.13. So this is how you can use normal distribution tables for control charts. And what kind of control chart can we draw? Actually, there are multiple control charts. For example, P chart, X bar chart, and R chart. And typically, there are 2 principal types of control charts. One is X bar chart, and the other one is R chart. And so in order for us to calculate the X bar chart, as we mentioned before, we need to know what are the limits, right? How do we find the limits? We actually have equations here, right? So for X bar chart, the upper control limit equals to X grand bar, or we can bar, plus, so this is the average of the average, right? Average of the average, plus A2 times R average. What is R? R is the range, right? Is the range for each sample, right? R is the range for each sample. X bar is what? X bar is the average of each sample, right? And we can have multiple samples, right? Have multiple samples, and X bar means this is the average of the averages, right? The average of all these averages for each sample. And if we have if we know the range, we know the averages, and then we also know the sample size. We can find this A2 from what? From this table, right? How do we determine the A2? It depends on the number of observations in each sample. So which means that the sample size, right? If we know the sample size, we can calculate, we can find the A2 value, and then we can calculate the upper control limit and lower control limit. This is the one is up plus, the other one is minus. Similarly, we can calculate the R charts, upper control limit and lower control limit, as long as we know the range, right? The average of the ranges, and also the sample size, right? D3 and D4. This is a D3, this is D4 value. Same thing, it depends on the sample size, right? All right, now let's look at one example here. So 8 samples, right? 8 samples, and each sample size is 4. Have how many data sets do we have? 4 times 8, right? Which means that 32 data has been collected, and they are put into 8 samples and 4 size of 4. From manufacturing process that is in statistical control, and the dimension of interest has been measured for each part, it is desired to determine the value of the center, the lower control limit, and upper control limit for X bar and R charts. The calculated X bar chart values, X bar, which is average, right? Average of each sample, it is given in centimeters for the 8 samples R. So these are the average of each sample. This is average of sample 1, average of sample 2, average of sample 3, right? Average of sample 8. Then the calculated R values, the R is the range, right? The range means the largest, if the size is the largest size minus the smallest size, right? Respectively, you can see these 8 values, right? This is the range for sample 1, range for sample 2, range for sample 3, and this is the range for sample 8. All right, now we have R value, right? We also have the averages, right? All average values. We know the sample size. We can find out what are the A2 values, D3 value, and also D4 values, right? Now we can calculate, right? This is X bar, grand bar is this value, then R average is this value. And then we can calculate, we can use that table to help us find out the lower control limit and upper control limit for the X bar chart. And then for the R chart, we can also find the upper control limit and lower control limit. And then what do? We draw a control chart. Remember, we already know the upper control limit. We already calculated the lower control limit and center line. Then we put each data points in it. How many data points? 8 samples, right? So there's supposed to be 8, right? Data points. Same thing with the R chart. Make sure for when you are drawing the control charts, you have to include upper control limit, lower control limit, center line, and also data points, as well as these labels. So that's control charts, X bar chart and R chart. Another chart I want to talk about is the P chart. So the P chart means that's the probability of the arrows. So either a good or bad, right? It's a yes or no decision. And how do we calculate the P chart? First, we need to know what is average of the P average. So P average means it's the number of defective divided by number of observations, right? Number of observations. And also we can use SB. This is the standard deviation equals to this equation. You can use this equation to calculate the standard deviation. All right, now upper control limit can be calculated with P average plus Z times SP standard deviation. Okay. Now let's look at another example here for the P chart. Say insurance company wants to design a control chart to monitor whether insurance claims forms are being completed correctly. The company intends to use the chart to see if improvements in the design of the form are effective. To start the process, the company collected data on the number of correctly completed claims forms over the past 10 days, right? Past 10 days, right? The insurance company processes thousands of these forms each day, a lot of forms, right? And due to the high cost of inspecting each form, only a small representative sample, right? The sample was collected each day. The data and analysis are shown in the table. So these are the samples. How many samples? 10 days, right? 10 samples. And each day, how many are collected? 300. Each day is only 300. But because each day thousands of forms are generated, we cannot just measure each one of those. We only collect a sample that is sample size is 300, right? And then we found out that for each sample, how many incorrectly completed forms. So these are the incorrect completed forms. Then we can calculate the average for the average of probability for each sample. This is the probability of defective parts in each sample. We call it fraction defective. And these are the probabilities. And first of all, if you want to calculate, if you want to draw the P chart, we first need to know what is the P average, right? P average equals to the total number of defective parts divided by the number of observations. How many numbers of observations we have? 3,000. How many total of defects? 91, right? 91 divided by 3,000, we get this 0.03033. And this is P average. And then next we can calculate the standard deviation, right? Standard deviation of the samples. Then we can use this equation to calculate the standard deviation of the samples. Then after that, we can find the lower control limit using P plus 3 times standard deviation. Why do we use 3 times standard deviation? Here is because say we want what? We want 99.7% confidence that process is within the limits, right? Suppose that we want a 99.7% confidence, right? That the quality are good, right? 99.7 of the forms are good. Then we can find out, okay, where is the Z value, right? Remember that normal distribution table, right? If it's on 99.7, then we need to find out the Z, right? How wide is this range, right? How wide is this range? All right, so because we know the probability, we can find the Z value, 3 gives us this probability. So that's why the Z equals to 3. And this is how we can find our upper control limit and lower control limit. Use 3 sigma, right? Use 3 sigma. So this is the P average plus 3 sigma and the P average minus the 3 sigma, got these values. Then we can use the value calculated to draw control charts, right? And this is a lower control limit, this is an upper control limit, and these are data points. You can also need to calculate the middle center line as well. Okay. All right. Another thing is when we are looking at control charts, how do we interpret our results? Right. It's not the case that if all the data points are within the upper control limit and lower control limit, they're good. Because you will see from these charts, some of those actually have very weird behavior that's going up or going constantly down or this, right? So we need to learn how to how to tell issues might happen, and it might go out of control. All right, typical normal behavior is that they all are around the center line, and you don't see any clear pattern. Right? You don't see any clear pattern of going up or going down. Well, if something happens, it can be like this, right? Some data points actually outside of the control limits. So it means that some attention need to be paid into to fix the issues. Well, some of the behavior will be like this, right? You have multiple points that is going upper, right? In the upper direction, and which means that maybe there's something going wrong that is making the the value is going up. Well, some may be like this, some may be like this, and sometimes you may see there's a certain trend, and then going up again, and then going down again, and then going up and then going down. So this is also shows that maybe something is happening with our process. Or sometimes you may see very erratic behavior of the points, right? So this is changes too much compared to the normal behavior. So if you see this happen, means that you also want to figure out what happened, right? To the process. And sometimes you may see, some data points that keep going low to a lower direction, which means that later it might just go out of control to the over this below this lower control limit. So make sure you know that how to recognize, how to tell something needs to be done, from the control charts. And this is also the reason that we are drawing control charts to help us, give us more visual understanding of the process. And lastly, I want to talk about a little bit about the quality control or quality program in manufacturing companies. Some of them you have learned before, for example, or you have heard before, for example, ISO 19000. So ISO 19000 mainly is about documentation or responsibilities or some emergency practices. And so basically, do you have a system, of implementing quality practices, right? So that's ISO 19000. Something to note is that ISO 19000 is actually very basic practices, and a lot of other factories, doing a lot more than ISO 19000. For example, some factories also have their own, Six Sigma programs. So Six Sigma focuses on solving problems and also the quality control. For example, if something happened, then you have a team of a Six Sigma team to conduct the make process, right? Define, measure, analyze, improve, control to analyze what happened, to develop some measures, and then to implement the measures, and then also control the process according to the revision or to the solution. And also there will be a total quality management you can look at. That is total quality management means that the quality is not just it's not just the operator's responsibility. It's actually everyone in the company's responsibility. From the executive leaders, right, from the boss to the management, and also to each of the operators, right? It includes executives, production managers, engineers, as well as operators. And everyone is taking responsibility on the quality differently, and that is a key philosophy. And total quality management actually started, after the the start of the rise of the Japanese quality practices, after Second World War. At that time, that Japanese cars, started to make really good quality cars. They became very competitive in the market, and a lot of products the same thing. And so to react to that, the American industry started to build some some programs to enhance their own quality and management. And one is led by NIST. So this Malcolm about the National Quality Award is to to give award who take really good quality programs, management programs in industry. And all right, so that's pretty much everything for this lecture.